VLDB is one of top 3 international conferences in the database industry. I'm very happy to note a multi-master paper on Huawei Cloud Database was accepted by VLDB. Today, it's a great honor to have the author of this paper, Alex, here. Let's go. Hello everyone, we are glad to have Alex here today to talk about multi-master. Hi Alex, please say hello to everyone.
Hello, nice meeting you. Thank you very much for inviting me here.
Welcome. Let's get started to talk about this paper. Why did you and your team choose this topic? Can you briefly introduce the background of this paper?
Of course, standard deployment of a large high-performance enterprise-scale databases include a single writer or master and multiple read-only replicas. However, having a single writer results in a single point of failure and also limits scalability. This introduces both availability and performance problems, two key aspects of a good enterprise-level database. This is why multi-master databases are in demand. There are two approaches to multi-masters: shared nothing and shared data. The first approach: each node performs compute and storage for a small subset of data. On a highly partitioned workload, this approach provides very high scalability, but the per-node cost is high. Even more important is that shared nothing approach functions poorly in workloads that don't have clear data partitions, change with time, or have hotspots. Availability problem cannot be solved by shared nothing approach as well. In the shared data approach, we have a separation between compute and storage layers. However, tight integration and intensive network communication of these solutions require high-end and dedicated network hardware. These solutions are designed to function on-premise, when cost is not an issue. They are not suitable for the cloud, cornerstone of which is high cost effectiveness, achievable by sharing infrastructure costs by multiple customers. Thus, key to the performance in the cloud is optimization for shared networks. And we focus on reducing network traffic both with respect to size and number of messages. This is what our work tried to achieve. It's not easy. A lot of companies tried this and didn't succeed.
How do we achieve multi-master in the cloud environment? What are the technology innovations?
First of all, we approached the problem by classifying the network traffic and found that major network consumers are write multiplication due to writing full pages, clock synchronization, and clocking messages. Then we tried to understand how to reduce traffic in each group. Let's talk about each source of overhead in details. First, regarding write multiplication. We already had a solution that addressed write multiplication, a single master solution that we have presented to the research community in 2020 in the SIGMOD conference, and that is currently available to customers. The second source of overhead specific to multi-master databases is clock synchronization. On a single writer database, using clocks is trivial. We can use an in-memory atomic counter, and it will be very fast, for example around 10 nanoseconds. However, in distributed systems, this counter will have to be accessed through a network, making latencies to be 10 to 100,000 times slower, making this naive approach not practical. The problem is not new. In the 1970s, Leslie Lampard invented scalar clocks. Each timestamp was composed of one number, and clocks were synchronized only during message exchange. His algorithm is simple and elegant, but it didn't allow creation of distributed snapshots of a database, which is very important for performance. Another invention came later and was called vector clocks. Vector clocks enable us to create distributed snapshots. A big disadvantage of the vector clocks was their size. Messages between databases are small, and vector timestamp doubles or triples the size of such messages, causing large network overhead. We have invented a new type of clocks, called VS clocks. The key innovation is that it can produce vector or scalar timestamps that are comparable with each other. And because we need vector timestamps significantly rarer than scalar, we get best of both worlds: small network utilization and ability to create global database snapshots. Finally, let's review the third source of overhead, namely log messages. Certain changes to a database need to be seen as atomic. For example, a modification to an internal database page or modification to user roles made by a transaction. Traditionally, in order to achieve this, databases used logs. We made an important observation that since all rows are stored on pages, a row can never be modified or read without the page on which this row resides being modified or read correspondingly. Thus, at the bottom of our hybrid row page logs is the idea to ship row logs information not as a separate message, but as a part of a page log. This reduces number of login messages up to 2 times, further reducing the load on the network.
Sounds cool. You just introduced 3 novel ways to reduce network consumption. How to implement and use them in our multi-master architecture?
Shipping log records reduces log data written over the network by 30 times. Hybrid logs reduce number of network messages by 30% on a typical workload. VS logs reduce amount of data sent over the network by 68% on an 8-master cluster. This amounts for 15 gigabytes per second of bandwidth savings for a write-only workload.
Compared with other vendors, what is our strength?
With respect to shared data databases, we have compared our approach with the only other cloud-native shared data database available. This database uses optimistic concurrency control to reduce network communications. However, this approach has a risk of conflicts, which results of one of the conflicting transactions to be aborted and work done wasted. In all tests, we observed that performance of our solution significantly higher than that of the other database. We could easily scale up to 16 masters, while the other database didn't allow more than 4 masters. Our solution handles workloads with small and high degree of data sharing much better. We have also compared performance of our solution with a database based on a shared nothing architecture. We have chosen a well-known open-source database that has demonstrated better performance than Spanner and TIDB. We deployed both databases on identical hardware with a configuration of 16 and 12 nodes. We ran the industry standard TPCC benchmark, and in all cases, our solution throughput was 60 to 300% higher with significantly lower transaction latency.
What is the industry influence of this paper?
Industry influence of this solution is very important, not only because it provides significantly higher performance and scalability, but also because it is applicable to other areas such as high availability and serverless computing, which is one of the cornerstones of the cloud computations.
As a team leader, can you talk about the challenges in the research of this paper and how your team to overcome these challenges?
Yeah, so there's a couple of challenges. First of all, no one has done the cloud-native shared storage-based multi-master project successfully before. The existing solution was designed for the traditional data center, which is not suitable for the cloud environment. This forced us to invent new approach and algorithm. Secondly, during the engineering process, the complexity of the system is immense and involve tens of nodes exchanging meaning of the message and serving meaning of the transaction per second across multiple components, which make system analysis and debug very challenging. We solve them by assembling a team of the world-class experts from different areas to overcome this engineering challenge.
What is the future research plan of your team?
In the short term, we're trying to work with the product team to learn some of the key technology of the multi-master to VLDB product. And in middle and long term, there are a few more research areas we are very interested in. including serverless database, cloud-native argument transaction, global database.